previous lecture, we had looked at the principle of virtual work for the model one-dimensional problem that we had introduced. We had also introduced the concept of the variation of a function, where u was our displacement function, and corresponding to u, we had defined the variation of u as del of u. We had also introduced a new concept of a functional, which, if you remember, was defined as the function of a function. That is, it would take a function and give us a number. So for different functions, we'll get different numbers. From the definition of this functional, we reposed our principle of virtual work as a minimization of a functional. And that functional we got corresponding to the model problem of interest turns out to be the total potential energy corresponding to the system. And we had said that the corresponding equations in the integral form that we obtained could be obtained by taking the first variation of the functional, that is del of pi, and setting it equal to 0. That is, we are looking for the function u which minimizes this functional pi. After we have done all this, we had also introduced the Ritz method as one of the techniques to get an approximate solution to the problem of interest. Now the question is, why do we want an approximate solution? As we had shown that most of the boundary value problems that we may be interested in will not have a readily available exact solution. That is, getting a closed form solution may be almost impossible. In that case, we would like to obtain an approximate solution to that problem. And in this one-dimensional setting, we would like to introduce all the concepts that are needed in order to obtain a good approximate solution using the method of our choice. And given this introduction, what we will do is we will develop the Ritz method that we had introduced last time in greater detail, and we will apply it to some typical examples corresponding to the model problem that we have introduced. And we will show how good or bad the Ritz method does with respect to the solution of these model problems. So essentially, we are creating an artificial situation where we would like to gauge how good the problem does, the Ritz solution does, or how bad it does, and let us see how we can improve the accuracy of the solution and what can be the causes of the solution being bad if we obtain it. So remember that our model problem was this bar problem, where the cross section of the bar was non-uniform and it is subjected to a distributed body force Fx constrained at the point x equal to 0, that is, the displacement is set to 0 at the point x equal to 0, and at the point x equal to L, a force P is applied. Under the action of this force P, this distributed load Fx and the constraint at the point x equal to 0, I would like to obtain the solution to this problem. So corresponding to the model problem that we have introduced, let us rewrite the functional that we are interested in, that is, I of u is equal to pi of u, which is equal to, in this case, integral, we will take from x equal to 0 to L, half in front, Ea u comma x whole square dx minus integral x equal to 0 to L f u dx minus p u evaluated at x equal to L. This is our functional. What we had said as far as the solution to the problem was concerned, the solution u corresponds to a minimum of this potential pi. So we said variation of pi of u is equal to 0, equal to, as we had defined the operation of variation for functions and as well as for functionals, this will be equal to Ea u comma x variation of u comma x dx minus integral x is equal to 0 to L f variation of u dx minus p variation of u at x equal to L. So remember that we had said that the variation of this quantity half of EA u comma x squared was as if I have taken the derivative of this expression with respect to u, and so we end up getting the half goes and we will get integral of EA u comma x variation of u comma x dx minus this. Given this variation, now what we will do in the Ritz method, as we had said earlier, we are going to look for an approximate solution of the following form. I will call it by the name un of x. This will be equal to sigma I is equal to 0 to n ai phi I of x, where we had said these ai's are the coefficients which have to be determined and phi i's are the so called basis functions that are used to define this series solution. Now what do we want? If you remember from what we had said last time, that the un of x has to satisfy the geometric boundary conditions or the essential or the Dirichlet boundary conditions, which means that we want this one to be at the point x equal to 0 to be equal to 0. That is, it is equal to the specified displacement at the point x equal to 0. Okay. This has to be satisfied by the un of x. Let us choose a particular set of these functions phi I of x. What does occur to us naturally? What are the things that we are used to? So let us take phi I of x is equal to x to the power of I for I going from 0 to n. So when we take this and substitute it in our expression, we will end up getting un of x is equal to sigma I is equal to 0 to n ai x to the power of I. Now we want un at 0 to be equal to 0, which is equal to, what do we get? By substituting 0 for x to the power of I, we will get a 0. So what we end up getting is a 0 is equal to 0. So this is the constraint that we have enforced. Okay. So now what we end up getting after enforcing the constraint at the point x equal to 0, we will get a series I is equal to 1 to n ai x to the power of I, because a0 has been determined from the boundary condition. Once we get this expression, now the question is, how do we obtain these coefficients? So let us go back to our variational formulation. Here if you see, we have ux and we have this variation of u comma x. So what we are going to do is, instead of u of x, we are going to substitute this with u n of x, and the variation of u will then become variation of un of x. So let us now define what is the variation of un of x. This will be equal to variation of sigma I is equal to 1 to n ai x to the power of I. These functions x to the power of I are given to us. What is going to change in order to get the variation is the coefficients ai. So the variation of un of x will become summation 1 to n variation of ai x to the power of I. Once we have obtained this expression for the variation of un, let us go and put it back in our variational formulation. So when we put it back in our variational formulation, we'll get delta of pi of un is equal to summation of I is equal to 1 to n Ea, which is a function of x, un comma x, and here we will end up getting variation of ai and d dx of x to the power of I. So what we have done, we have substituted instead of variation of un in the expression, this summation. Then we will also get minus integral x is equal to 0 to L summation. Now I have to take the summation out. Anyway, I'll put it here. Variation of ai into f multiplied by x to the power of I, the whole thing dx, and finally we'll get the term minus p x to the power of I evaluated at 1 at L. So this is the whole expression that we'll get by substituting for variation of un in our variational formulation. So now let us again rewrite the whole thing. We'll get implies summation of I going from 1 to n variation of ai into, we'll put the big brackets, integral x is equal to 0 to L Ea un comma x d dx of, I am going to replace xi by phi I. One should understand that in our example that we have taken, x to the power of I is our phi I dx minus integral x is equal to 0 to L f phi I dx minus p into phi I evaluated at the point L. This whole expression is equal to 0. Next what? So how do we get now the equations using which we can determine the unknown coefficients ai? That is our goal. So then you look at this variation of ai. Now this is something that is under our control. The variation is in a way an abstract virtual displacement that I am giving to the structure which is already in equilibrium. So I can choose what kind of variation I give. So in a way what I am saying is that we can vary each of these AIs independently, i.e. these are independent coefficients. That is, the variation can also be done independently. Okay. So let us take, for example, that I decide to choose variation of A1 is equal to 1, while variation of all the other AJs equal to 0 for j is equal to 2 to n. So let's put it back in this expression. When we put it back in this expression, this summation gives us what? It gives us, by putting the value of variation of A1 is equal to 1 and all the other variations equal to 0, we will get integral x is equal to 0 to L Ea un comma x. I will write phi 1 comma x dx minus integral x is equal to 0 to L f phi 1 dx minus p into phi 1 evaluated at x equal to L is equal to 0. Remember what we have done? We have taken the variation of A1 is equal to 1. All other variations we have set to 0. That is one choice of the variation that we have taken. That is, we have taken del un of x is equal to 1 into phi 1 of x. Okay. when we substitute this choice, we get this equation. So let us now expand this equation in terms of the coefficients ai. So what we'll do is when we put it there, you'll get integral x is equal to 0 to L Ea sigma j is equal to 1 to n aj phi j comma x phi 1 comma x dx minus x is equal to 0 to L f phi 1 dx minus p into phi 1 at x equal to L. So let us now take the summation out. We'll write implies summation of I is equal to 1 to n, sorry, I had put j. So let us put j, aj integral x is equal to 0 to L Ea, what will we get? Phi j comma x phi 1 comma x dx is equal to, by taking the other part to the right hand side, integral x is equal to 0 to L f phi 1 dx plus p into phi 1 evaluated at x equal to L. So I have taken the other part to the right hand side simply because you see that f is a known, the phi 1 is a known, p is a known, and phi 1 at x equal to L is also known because we know the expression for the phi 1, which is nothing but x. So x evaluated at L we know. So all the knowns have been brought over to the right hand side. What is the unknown? Unknown is aj, which remains on the left hand side. So now look at this expression. This is a number because Ea we know, phi j we know because we have chosen the phi j's, and the phi 1 we know. So we put all of those into this expression of the integral. This will turn out to be a number. This number we are going to give a name. We will call it k1j. Why do we call it 1j? Because you see that everything, this phi j comma x is multiplied by phi 1 comma x. Okay. So for the different phi j's, we are always multiplying with phi 1 comma x. So this is the first index, and the second index comes because of this phi j sitting there. If I write it now in this index form, I will get implies summation of j is equal to 1 to n k 1j aj is equal to, look at this now on the right hand side, this f is not going to change if we change our phi i's. So this f will remain fixed as a function. So f into phi 1 integral over x equal to 0 will be a number corresponding to phi 1. Similarly, p into phi 1 at x equal to L will also be a number corresponding to phi 1. So we are going to call this as f1. So this is one equation that we get. So then what we can do is, similarly, we can choose the other delta ai's one by one equal to 1 and keeping the other ones 0. That is, we will say that we will take delta ai for a particular I is equal to 1, and for all others for j not equal to I. This will be a particular choice of these varied parameters. For this particular choice, if I go now to the equation, then we can generalize what we have done corresponding to the phi I that we have taken, or the delta ai that we have taken. Sigma j is equal to 1 to n aj integral x is equal to 0 to L Ea phi j comma x phi I comma x dx. This is equal to integral x is equal to 0 to L f phi I dx plus p phi I evaluated at L. So again, you see this expression here, the j is going from 1 to n, that is we are summing over the j's, but this I is fixed. So what we can write here is, we can replace this by coefficient k I j. So this integral becomes the coefficient or a number k I j. Similarly, this one, where corresponding to the choice of delta un equal to 1 into phi I, we'll get this one as f into phi I integrated plus p into phi I at L. So we'll call this by a name fi, which is again a number. So what we'll get as the equation, j is equal to 1 to n kij aj is equal to fi. Now for I going from 1 to 2, that is for each of these i's we'll get an equation. So now what we have is a system of linear equations or simultaneous equations in terms of the unknown coefficients aj. This we can write in matrix form. This we can write in matrix form as matrix K operating on the vector A is equal to the vector F. You look at this matrix K. This matrix K is of size n by n for the problem that we have taken. This is a vector of size n, that is it has n coefficients a1 to an. This is a vector of size n. This matrix, as we will see, can be called the so-called stiffness matrix. This vector, we are going to give it a name called the displacement vector, and this vector will be called the load vector. So now we have this matrix problem Ka is equal to F, which, if it can be solved, will give us the unknown coefficients A. So once I obtain the unknown coefficients A, then I know the expression for un of x. Okay. Now let us look at this matrix. What are the entries of this matrix? So Kij, if I look at the elements of this matrix, that is the element sitting in the ith row and in the jth column will be equal to integral x equal to 0 to L Ea phi j comma x phi I comma x dx. Now I ask you the following question. Tell me, what is the element sitting in the jth row and the ith column? That will be obtained by bringing this here and bringing that there. The expression is not going to change because the integrand remains the same. So what we get for this case is that this thing is equal to Kij. So what does that mean in terms of the matrix notations? It means that the matrix K is symmetric. That is, when Kij is equal to Kji, we have K is equal to K transpose. Secondly, if we look at the following expression, half of A transpose Ka. So let's imagine I give you a set of these coefficients A, and then I would like to evaluate this expression. What is it equal to? This will be equal to, from what we have already defined, half of integral x is equal to 0 to L Ea into u bar n comma x whole squared dx, where I am going to call u bar n as a function of x is equal to summation I is equal to 1 to n ai phi of x. Now tell me, this integrand is always greater than 0 when these coefficients ai are not all equal to 0. So which means that when this function un is not the trivial function, that is unx is equal to 0 everywhere, then this expression has to be greater than 0, this integrand, because I am looking at u bar comma x whole squared. So when this integrand is greater than 0, what do we have? That in that case, this expression itself, this half A transpose Ka is greater than 0 for, I will say, non-trivial A. Okay. So what does that mean? That if I give you any choice of this set of coefficients A, I can guarantee that if these A's are not all equal to 0, then this expression half A transpose Ka is greater than 0, which means that this matrix K is positive definite. So the definition for positive definiteness of a matrix is that if I give you any set of these vectors A which are non-trivial, then A transpose Ka has to be greater than 0. And if we look back to the expression that we have taken, that the integral that corresponds to this expression A transpose Ka is nothing but twice the strain energy of the corresponding to the displacement given by u bar n. And for a structure, we know that the strain energy cannot be 0 or negative unless the structure is subjected to a rigid body motion. Here we don't have any rigid modes, so which means that for any A which is non-trivial, this is greater than 0. Why do we need this positive definiteness of the matrix? Positive definiteness ensures that this matrix K is invertible. This was not obvious by looking at symmetry. A matrix can be symmetric but may not be invertible. It could be singular. But by this proof that we have shown that yes, indeed, for our Ritz formulation of the model problem that we have taken, indeed this matrix K is positive definite, which means that whatever be the n, we can always invert the matrix K. Why is it important? Because if we can't invert K, then we cannot get the solution vector A, which is given by K inverse F. So once we guarantee invertibility of the matrix, then the solution vector A can be obtained. So once we have obtained the solution vector A, then now we put it back in our expression for the solution, which is, at least in our example, it is AI phi of x, where AIs are now known. So this is how we construct a typical Rayleigh-Ritz or Ritz solution to a given boundary value problem. Now there can be interesting offshoots to this problem. I mean, this is not the only model problem that we may be interested in. Let's say that I want to solve this problem. Okay, let's say I want to solve this problem. That is, there is this bar subjected to a constraint u at 0 is equal to 0 and a constraint u at L is also equal to 0. This could be a problem of interest. Now in this case, how do we go about constructing the Ritz approximation? So you see that in the earlier case it was very easy to enforce the geometric conditions at the point x equal to 0. Now we have to enforce the geometric conditions both at the points x equal to 0 and x equal to L. So how are we going to do this job? So we will take again un of x, we will say it is equal to something called phi 0 bar of x plus summation of I equal to 1 to n ai phi I of x, where this phi 0 bar has a job of satisfying both these end conditions, and the phi i's will be such that phi I at 0 is equal to 0 and phi I at L is equal to 0. So what we are going to do is, we are going to choose the phi i's in such a way that they satisfy the 0 condition at both ends, while the phi 0 bar takes care of the 0 displacement condition at the two ends. You see that in all problems you may not have the 0 displacement condition. You may have this one as some number delta 1, this one as some number delta 2. In that case, phi 0 bar at 0 has to be equal to delta 1 and phi 0 bar at L has to be delta 2, while the phi i's will satisfy the conditions of 0 value at the two ends. So in this case, let us say that my u at 0 is equal to delta 1 and u at L is equal to delta 2. Then how do we construct this function phi naught of x? It is very easy. You take it to be delta 1 into one minus x by L plus delta 2 into x by L. So if you look at this expression, what happens at 0, at x equal to 0, we will get x by L equal to 0 and this other expression is equal to 0. So at this is going to give me phi 0 at 0 is equal to delta 1 and phi 0 bar at x equal to L. If you substitute, then this expression is going to go to 0. What we are going to get here is 1. So this will be equal to delta 2. So phi 0 bar satisfies the given geometric constraints exactly at the 2 points. Now then the question is, how do I choose the remaining phi i's? In the expression for the un of x. So phi 0 bar is completely known. We have to get these phi i's. So one option, if you remember, that phi I has to be 0 at x equal to 0 and at x equal to L for this particular case that we have taken. So in this case, what choice can be made for phi I? So the first function phi I can be, it has to be a quadratic, right? Because a quadratic is the only function which is going to, the minimum order polynomial which is going to vanish at the two ends. So this can be made x minus 0 into L minus x. So I can make phi 1 of x is equal to x into L minus x. These are all choices that we can make. Similarly, phi 2x will be now a cubic. So it could be a function going like this. So I can take it to be, I am just choosing things according to my wish. So L2 minus x into L minus x. So what I want this function to do is, it should vanish at point x equal to 0, at the point x is equal to L by 2 and the point x equal to L. So I get a cubic expression, x into L by 2 minus x into L minus x, and so on. I can keep on constructing these phi i's, which are functions of increasing order polynomials, by choosing appropriate points where they vanish. Once I have done this construction, then I will put it back in my expression for un of x to get un of x will be equal to phi 0 bar plus 1 to n ai phi I of x. Now our job will be again to find these coefficients ai. So we will substitute this back in our variational formulation. The only thing that you should observe is this variation of un of x will be actually equal to variation of phi 0 of x plus summation I is equal to 1 to n variation of ai phi I of x. Now this phi 0 of x is a known fixed function, that is, we know what it is. So the variation of phi 0 of x is 0. So what we'll end up getting is variation of un is nothing but summation from 1 to n variation of ai phi I of x. So by putting it back in the principle of virtual work or the variational formulation that we have made, and by choosing particular values for this delta ai's, we will get now n equations in terms of the n unknown coefficients ai, exactly the way we have done earlier. The only difference will be that your un will carry this expression. So let me just write it down to make things clear. So the ith equation I will just write. The ith equation will be summation of j is equal to 1 to n aj integral x is equal to 0 to L ea phi j comma x phi I comma x dx is equal to integral x is equal to 0 to L f phi I dx plus p phi I evaluated at x equal to L plus a part which will come, remember, from your un of x. Which part? Un of x was equal to phi 0 comma x plus the remainder part. This part is a known, so this will also go as not as a plus but as a minus. So we'll get minus integral x is equal to 0 to L phi 0 bar comma x into phi I comma x into ea dx. This part is coming from the known function phi 0 bar, which satisfies the given boundary condition. This is the additional correction that we have to do to our variational formulation in order to account for this phi 0 bar of x. So now we have the n equations again in terms of the n coefficients. This expression will be nothing but kij, and this whole thing on the right hand side will be our f of I. We go ahead and solve this problem and get the solution, that is the coefficients ai. So this is how you would construct the Rayleigh-Ridge solution for a variety of problems with different boundary conditions, different load vectors, different material coefficients using a polynomial approximation. Now nobody tells us that we should use a polynomial approximation. We can also use the sine cosine functions. For example, we could have chosen the phi I of x is equal to sine n pi x by L. Very easily we could have done this, though our phi 0 of x would have remained equal to delta 1 into 1 minus x by L plus delta 2 into x by L. But these phi i's for I equal to 1 to n, I could have chosen these, and in terms of these functions, which are trigonometric functions, we could have again obtained a series solution, okay, by following the same procedure. Let us now look at an example. with which we will demonstrate how this Rayleigh-Ridge method is used and what is the solution that we will get. Let us take this problem. Bar again, okay, with an end load P is equal to 10 and subjected to a distributed load of uniform intensity, that is, we will say f of x is equal to 1, and we will say, you see this is a fictitious problem, we will say EA is equal to 1. So in this case, if you look at the differential equation, it becomes minus d2u dx squared is equal to 1 for x lying between 0 and 1. We have taken the bar to be of length 1, and we will say that u at 0 is equal to 0. At the end x equal to 1, we will have EA du dx, where EA now is 1. So you will have du dx at the point 1 is equal to 10. So corresponding to this one, if we now go and choose our phi i's as we have done earlier, is equal to x to the power of I, okay, and we will take a two-term solution. Let us take n equal to 2. Then our u2 of x will be equal to a1 into x plus a2 x squared. So going back to our virtual formulation and writing the final matrices, I will get k into A is equal to F, where k will have entries 1, 1, 1, 4 by 3. You should all evaluate these entries to convince yourself. A1, A2, this is going to be equal to the load, which is equal to 31 by 3 and 41 by 4. So when we solve this, we will end up getting A1, A2 is equal to 127 by 12 and minus 1 by 4. So our u2 of x will be equal to 127 by 12 x minus 1/4 x squared. This will be our Rayleigh-Ridge solution, taking two terms in the polynomial expansion. Similarly, if I now take three terms, that is, I would like to have u3 of x is equal to a1 x plus a2 x squared plus a3 x cubed. And again we go through the same exercise. We will get the matrix A k as 1, 1, 1, 4 by 3, 1, 6 by 4, 9 by 5. This 6 by 4 also has to be here, 1 because it is symmetric. This into A1, A2, A3 is equal to F1, F2, F3, where F1, F2, F3 can be evaluated from the integrals. We will end up getting the coefficients. A1 is equal to (10.5), A2 is equal to 0, and A3 is equal to minus 1 by 6. So our u3 of x will be equal to 10.5 x minus 1 by 6 x cubed, and you will see that this is the exact solution of this problem. The exact solution of this problem turns out to be a cubic polynomial, and by taking 3 terms in the series expansion, we have exactly captured it, which had to happen. There is no other thing that we could have obtained, because we have said that these phi i's should be able to completely represent the highest order polynomial. That is, in this case, the linear combination of the 3 phi i's should be able to exactly capture a cubic polynomial, and here the exact solution was a cubic polynomial which we have captured. If you get 10.4x minus something, your answer is wrong. Then you should go back and check your calculations. This answer should be correct to the last decimal digit. So now let us look at the plots of this expression. Both these expressions, the 2-term solution and the 3-term solution that we have obtained. Okay, whenever we obtain an approximate solution, we should again look back at what is the goal of this whole computation. The goal is to obtain response quantities of interest to a sufficient level of accuracy. So let us look at this graph that we have plotted of the displacements for the 2-term solution and for the 3-term solution as a function of x. So you see that here you can hardly see a difference. The two graphs almost overlap, that is with the exact one. Let us now see what happens when we look at the derivative information. When we look at the derivative information, then obviously the 3-term solution will overlap the exact one because it is the exact solution, while the 2-term solution does not do a great job with respect to the derivative, though it is not very far. If you look at the end values, you will get an error. If you look at this point, error in the range of 1%, 2% in the value of the derivative. But still, this, if you look at the derivative information, that is inferior to the accuracy of the value itself. This is going to be a feature of all approximation methods. That is, if we see a good accuracy with respect to the function itself, if we go on taking higher and higher derivatives, the accuracy is going to decrease. That is, we are going to pay the penalty by taking the derivative of a less accurate function. Okay, so once we have seen that this Rayleigh-Ridge method seems to be doing a great job for the problem of interest, then why go to anything else? We can stick to the Rayleigh-Ridge method and go along and solve all our boundary value problems using the Rayleigh-Ridge method. So let us see an example of a boundary value problem where the Rayleigh-Ridge method may not do well. Let's take a very simple problem. Again, our axial bar, it is our fictitious example that we have created with an end load 10. This is a bar of length 1. Now at the point x equal to half, I am going to apply a concentrated load F is equal to 20 units. This is at the point x is equal to half. So if I write the total potential energy corresponding to this problem, what will we get? Again, putting EA is equal to 1. We will get pi of u is equal to half integral x going from 0 to L u comma x whole squared dx minus 10 u evaluated at x equal to 1 minus 20 into u evaluated at x equal to half. So work done by the external forces is nothing but the work done by these point loads that have applied at the point half and 1. So if I do the variation of pi of u, we will again get integral x is equal to 0 to L u comma x variation of u comma x dx minus 10 variation of u evaluated at the point x equal to 1 minus 20 into variation of u evaluated at the point x equal to half. So let us now use the same approach that we had taken earlier. That is, we'll take the phi I of x to be equal to x to the power of I. So we can again take, let us take a two-term solution n equal to 2. So what we'll get, u2 of x is equal to a1 phi 1 plus a2 phi 2. Substitute it back in our variational formulation and get the equations corresponding to a1 a2 by what we have done. So what we'll end up getting is 1 1 1, that is the same stiffness matrix that we had obtained for the previous example, because the material has remained the same and the phi's are also the same. So there is no reason why the stiffness matrix should change. This will be equal to the load vector. Load vector is what? If you remember, it will be P into phi 1 evaluated at 1 plus F into phi 1 evaluated at half, and here it will be P into phi 2 evaluated at 1 plus F into phi 2 evaluated at half. Okay, so we will get, again if I rewrite, 1 1 1 4 by 3 into a1 a2 is equal to P into phi 1 evaluated at 1 is 10 plus F into phi 1 evaluated at half. So x evaluated at half is half, so 10 plus 10 you will get. Second one, P into phi 2 evaluated at 1, so phi 2 at 1 is equal to 1, so I will get again 10 plus F into phi 2 evaluated at half. Phi 2 is x squared, evaluated at half is 1/4, so 1/4 into 20 will give us 5. So this will be 20 and 15. Okay, so out of this, the coefficients a1 and a2 will come out to be equal to, when you solve this problem, will be equal to 35 and minus 15. That is, u2 of x is equal to 35x minus 15 x squared. Can you tell me what is the exact solution to this problem? The exact solution to this problem will be obtained in two parts. I am just drawing the bar here. This is F and this is P. Okay. So what will you get if you cut anywhere here from our standard mechanics of solids? We'll get EA du dx in this region up to this point x equal to half is equal to 10, implies du dx here is equal to 10, which is a constant. So u, I'll call this part as part with solution 2. So u2 of x will be equal to, I can write it as a2 plus b2 into x minus half. I could always write it as a linear because the slope is a constant, where b2 will be equal to 10. Similarly, if I look here in this part, I will call the solution as u1. Okay. So u1 of x will be such that I will get the slope equal to what? Slope will be equal to f plus p, which is 10 plus 20, which is 30, 30x. So u1, if I impose the condition at 0 is equal to 0 is equal to a1. So u1 will be equal to, as a function of x, 30x. Now we have to obtain a2. How do we obtain A2? By enforcing the continuity of the displacement at the point x equal to half. That is, u1 at half is equal to u2 at half. So this is going to give us 30 into half is equal to directly A2, which is equal to 15. So A2 becomes 15 plus 10 into x minus half, and u1 becomes 30x. Now, if you plot this function as a function of x, so in the first part, the slope will be 30 up to the point x equal to half, and beyond the point x equal to half, the slope will be 10. So up to the point x equal to 1. If you now take the solution that you have obtained using the Rayleigh-Ritz method, it will do something like this. So this is the exact and this is the Ritz. 2 term. If you take 3 terms, it will still do this. That is, what you are going to get as a solution is a polynomial. So at this point x equal to half, you will not be able to capture the change in the slope using the Rayleigh-Ritz solution. Whatever you do, your function may come close in terms of the values at the points, but the derivatives will be completely off at the point x equal to half, because this function is going to get a change in slope at the point x equal to half. So as an engineer, that is a cause of worry, because this will be one of the points where I would like to know what is the derivative. That is, I would like to know what are the stresses, such that I can decide whether this point is going to be safe or not. But our Rayleigh-Ritz solution is not going to give us the derivatives very accurately here, and we'll end up getting a very bad information regarding the state of stress at the point in the vicinity of the point x equal to half. The question is, why did the Rayleigh-Ritz method go wrong here? Answer is quite obvious, that here in the Rayleigh-Ritz method we are trying to fit a polynomial over the full domain, while the solution, as you have seen, is a piecewise polynomial. That is, in the region x equal to 0 to half, it is a polynomial, which is in this case a linear, and in the region half to 1, it is also a polynomial which of a different slope, which is also a linear. So somehow in our approximation, in the choice of these phi's, we have to build in this kind of an information, that is, we should choose phi's which can reproduce functions which are piecewise defined. That is the motivation of using the finite element method. I would say one of the motivations. In the next class, I am going to highlight this point a little further, elaborate on it, and make a case for using the finite element method, where we will say, okay, what do we do in order to rectify this kind of problems.